Okay, so let's get started. Yes, today I have a slight cold, so let's see if my voice can carry me through this lecture or not. I'll try my best. I hope now that you have been assigned to a project group and that you have scheduled a meeting with the TAs to get started. There will be some fluctuations in the groups here in the beginning because we are not sure exactly who's following the course or not. But hopefully we can converge very, very soon, and then we can start to get going on the projects. Actually, after today, I think you should be ready to. I mean, we covered enough material to get started on the projects, and there is no reason why not to get started earlier in these projects. Okay. So today we will talk more about physical layer, spectral efficiency, one-shot minimum distance receiver, matched filter, and signal constellations. And if we have time, we'll also cover a little bit on white Gaussian noise. We are actually a little bit ahead in the lecture plan, which is good because we have some material that I think needs a little bit of expansion later in the course. So we'll just keep on, at the pace we feel is comfortable. But that means also that sometimes the material between the lectures will shift somewhat. I hope that is okay with you. I will try to keep ping pong reasonably updated in this respect. Okay, very short review. What we talked about last time was quite a lot about these pulse amplitude modulators. And these are the workhorses of physical layers. It's a way of representing bits as signals, and it's a two-stage process. First, a mapping between a number of bits into a symbol, or actually an amplitude in this case. Amplitude and symbol are synonyms here. They mean the same thing. And a mapper example would be something like this. We have a number of bit patterns here of length k. So if we have k bits, we need 2 to the power of k possible signal alternatives. So we need then 2 to the power of k amplitudes. So each bit pattern maps onto one amplitude. And these amplitudes are then used to multiply with the basic pulse shape. And these pulse shapes are output from the modulator here once every t seconds. So every t seconds we output an amplitude, which means that every t seconds we output a number of bits here, namely k bits. So if we want to calculate the important rates here, there is a symbol rate here, which is 1 over t. It's the time between consecutive pulses. Okay, every t seconds we output one amplitude multiplied with one pulse here. And each of those amplitudes carries k bits, or if you like, the log 2 of m is also k. So the data rate, the number of bits per second that we are transmitting, is the log 2 of m divided by t, or the log 2 of m times the symbol rate. So bit rate here is faster than symbol rate in the general case. The only time when we have equality here is when we transmit exactly 1 bit per pulse, and that is when m is equal to 2. Log 2 of m is equal to 1. And here we have a bunch of definitions here. So then we talked a little bit about the properties of the pulse shape g here in order for things to work well. And we said that what is a good choice of G depends on what we do at the receiver. And at the receiver, what we always do at the receiver, regardless if it's for PAM or something else, is that we introduce a receiver filter. That's the first thing that happens in the receiver. So if we have then a transmitter here that has a pulse amplitude modulated signal at this point, we can think of this as the beginning of the receiver. So if we have a receiver here, with the linear filter with the impulse response f, then the output from the receiver filter can be written in this form, which is a pulse amplitude modulated signal, where we have the same amplitudes as we had for at this point. So the same amplitudes here, and the only thing we have done is to replace the pulse shape G to H, where H is now the convolution between G and F. Okay? So as soon as we filter a PAM process, we get a new PAM process, but with the new pulse shape. Okay? So it's very, very simple. Right? Every filtering step, just change the pulse. And what it is the original pulse convolved with the impulse response of the filter. Okay, so a common receiver looks something like this. Here, the transmitted signal at this point, we add some noise to it from the channel, and here's the receiver, and we have a receiver filter, and this is Y, the output of the receiver filter, and we sample that with the same rate as we sample that with symbol rate. That is, we sample this every t seconds, where t is the time between consecutive pulses. Okay. So in the best of worlds, what we would like to have out here, y-OK, is that it's actually equal to a-OK, because a-OK is the data. So if y-OK is a-OK, then we have perfect transmission. There are two things that are going to mess this up. One is the noise, and let's ignore that. So we take out the noise and just concentrate on the other thing that can mess up things. And what that is what's called intersymbol interference. Because if we look at this yk here and express that out find an expression for this, we see that the output sample yk here is equal to ak, which we're looking for, times a constant, which is the pulse shape's amplitude at time 0, plus this sum here. And this sum we don't want, okay? We think of that as interference, something that we would like to get rid of, okay? So this is what messes up our ability to communicate at this point. This part here depends on the pulse shape, and it depends on the transmitted symbols, okay? So it's something that varies depending on what symbols we transmit, and therefore it's called intersymbol interference. Now, we're interested in AK, we're not interested in the other symbols at this particular point in time. The next sample we take, we're interested in another symbol, but we're only interested in one symbol per sample. Okay? So that's the setup here. So if we want to get rid of this part here, we can do that by making sure that H has certain properties. Namely that its t-spaced samples are all 0. Okay? We see that here, what's in the sum here, k is an integer, m is an integer, k minus m is an integer. So here we have an integer times t. So we have t-spaced samples of H. If all of those are 0, then all of these terms are 0 and the whole sum is 0. Okay? So that's something that we would like to achieve. So ideally, the pulse shape is such that if we take samples of H every t seconds, all of them are 0 except one, and that is when t is equal to 0. Okay? Because that is in here, right? And this one we want to be non-zero. So we want this to be non-zero. It could be any number as long as we know that number. But for simplicity, we can just put it to 1 for the time being. Then we would simply just have AK here times 1 plus 0. And then YK will be equal to AK, and everything is perfect. All right. So this condition here is nice to have because it makes sure that the intersymbol interference is 0, and we can do perfect communication in the absence of noise. We still have noise to worry about, but we'll worry about that later. Okay, so this expression here, this is equivalent to an expression, or this condition in time is equivalent to this condition in frequency. Recall now, what we want to do, we want to design H so that it performs well. So either we design it in time, or we design it in frequency such that it fulfills this criterion. And what this criterion essentially is that we take the spectrum H here, capital H is the Fourier transform of small h. We basically take that and repeat that at various points along the frequency axis, add up all those spectra, and when we sum them together, if that happens to be a constant, then we're in business. Okay, so in order to figure out whether we have 0 intersymbol interference, we can do that in two ways. Either we look in the time domain and check for this condition, or we look in the frequency domain and check for this condition. Which one to choose? Depends, right? Depends on what's simplest. We have two tools and we use the best one. Okay. From this condition here, one can draw a few conclusions about the possibility to avoid intersymbol interference as it depends on the symbol rate and the bandwidth we have to our disposal. So, suppose G is band limited to W hertz, okay, and that's something we typically want, especially in radio, to have band limited transmitted signals in order to conserve spectrum. So if that is the case, then if the symbol rate exceeds 2 times W, then there is no way to avoid intersymbol interference. We cannot choose H in any way to avoid intersymbol interference. If the symbol rate is exactly twice the bandwidth, then it's possible, but it's only possible for one particular choice of pulse shape, namely when the convolution of G and F is a sinc function. That's the only choice. Now, when the symbol rate is a little bit less than twice the bandwidth, then it's possible to avoid intersymbol interference, and it's possible to choose many different H to achieve this. Okay, and we will see a few of those today, or one family of those. Okay, so this is nice. So one can say that the bottom one here, that is the practical operating point. That is, we sacrifice a little bit of symbol rate in order to get some freedom in choosing pulses. Now recall, of course, ideally we would like to communicate as fast as possible with the highest bit rate, data rate, and the data rate depends on the symbol rate times the number of bits. The bit rate, the data rate, is the symbol rate times the number of bits per symbol. So if we can increase RS, that's good. But we see here that we are upper limited by twice the bandwidth. We cannot communicate quicker than twice the bandwidth, otherwise we have to live with intersymbol interference, and that typically we want to avoid. And we want to avoid it for mainly one reason, and that is because the receiver becomes then much more complicated. Okay. And also from a theoretical point of view, there is no reason we cannot build a better receiver if we have intersymbol interference than without it. So there are two reasons why we want to operate in this domain here. Okay, now going back to the case when G is not band limited, for instance when it has a duration which is t seconds, then it's enough to choose a receiver filter which also has a duration of t seconds or less, and then we don't have any intersymbol interference. So, two things here. If we are band limited, we want to work below twice the bandwidth in symbol rate. If we don't care about bandwidth, we can pick any G which has a duration which is less than t, any F that has a duration less than t, and we're still in business. Okay. So two choices here. Now, for radio, we really want to be here. For cables, maybe we can live with this also. But yeah, okay. I'll leave it at that. Okay, so in the practical situation, we are actually operating with a symbol rate which is a little bit less than twice the bandwidth. Okay, and that is because to limit complexity of everything. Okay, so. Our practical operating point is then that we have the symbol rate, RS, which is less than 2W. Okay? And W is the bandwidth which is possible or desired. Okay. So this means, of course, that W here must be greater than RS divided by 2. Right? Or if we want to put this in terms of T, it's the RS over 2 is 1 over 2t. T is the time between consecutive pulses. Okay, so W is something, a number which is larger than 1 over 2t. And one way to write an equation for this is to say that W is equal to 1 plus alpha times 1 over 2t, where alpha is greater or equal, greater or equal to 0, right? I mean, we can always find an alpha to fulfill this equation. So, okay. And this equation we can write as 1 over 2t plus alpha over 2t, like this. And the reason for doing this is that W, the bandwidth we use, would be determined by the symbol rate we are working with. Or the other way around, if we have a fixed bandwidth, that would determine the symbol rate, which is maybe the more practical case. So 1 over 2t here is the minimum bandwidth needed to support ISI-free transmission at rate RS 1 over t. Right? That's basically just this condition here. So we can interpret this part here as the extra or excess that we actually use. And the reason why we put in some extra bandwidth here is to make life easy for us, so we can get some freedom in selecting pulse shapes. The spectral efficiency let me write this here. Okay. The spectral efficiency is a super important concept because it tells us how efficient we are in using spectrum. Okay, it comes from the name. And how to measure that is the number of bits per second that we can transmit per unit bandwidth. Okay, so we calculate the spectral efficiency. First of all, we have a symbol for that, which in this course is nu. Eta is also used in the literature. But the spectral efficiency here is simply the data rate, which is RB, in bits per second, divided with the bandwidth we are using, which is W. And this spectral efficiency, we typically, okay, so this is the definition of spectral efficiency. So when I put the triangle over the equal sign, it means definition. By definition, this is the case. And we typically say we have a certain spectral efficiency in bit per second per hertz. Okay, so that's what the unit for this. Now, bit is dimensionless unit. Second divided by hertz, that's also second multiplied with hertz is also dimensionless. So this is really, the spectral efficiency has no dimension, but to give it some meaning, we say it's the number of bits per second we can transmit per hertz. Bits per second per hertz. Okay? And we want that to be high. Right? We want to transmit as many bits per second as we possibly can in the bandwidth we have to our disposal. Now, if we use W according to this formula, which has the minimum bandwidth required plus some extra excess bandwidth, what is then the spectral efficiency? Well, it's easy enough. We calculate then using W equal 1 plus alpha over 2t, this formula. We see that this is 1 plus alpha divided by 2 times RS. Right? 1 over t is the symbol rate. So then we can write eta as the bit rate divided by W. And if we want to express the bit rate in the symbol rate, what would we do then? The bit rate is equal to blah, blah, blah symbol rate. What is blah, blah, blah? K, absolutely. So I like a fancy name for K, so I write the log 2 of M. K is the number of bits per symbol times the symbol rate, RS, and then we divide by W. And why do we write it like that? It's because we have here a relationship between W and RS. So we simply divide through by W and then, okay, well, we can solve this easily enough. So we have here the log 2 of M times 2 divided by 1 plus alpha is the final result. You agree? Okay, so if we want to have high spectral efficiency, what should we do? Well, we should either increase M, right? Or we should decrease alpha. Agreed? Okay, and alpha is a number which is greater than 0. So the best alpha we can choose in this respect would be alpha equals 0. Okay, and alpha equals 0 means that we are using the minimum bandwidth that we can, right? That if we put in alpha equals 0, the bandwidth is 1 over 2t, so twice the symbol rate divided by 2. Okay, so in all practical cases, we need alpha a little bit greater than 0, but we don't want to make it too large, right? Because then it will hurt us in spectral efficiency. Log 2 of M, we can increase that, but there are some deficiencies, there are some problems with that, and we'll see that later on. Essentially, there are two things. The receiver complexity goes up, and our sensitivity to noise also goes up. Okay, so we are actually limited in the choices we can make for M. Okay, but we're still not bothering with M or noise right at the moment. If we just look at alpha, what can we do? Well, we can, of course, choose alpha as small as possible. Okay, but we still don't want intersymbol interference. Okay, so the question is, can we find a set of pulses, a family of pulses, where we can change alpha, the excess bandwidth, and still remain, have a transmission scheme without intersymbol interference? And yes, we can do that. And the standard way to do that is to use a bunch of pulses who are known as raised cosine pulses. Okay, so I will just show you the equations and then draw this for you. So raised cosine pulses, what that really means is that these are pulses whose spectrum, that is, whose Fourier transform, is a raised cosine shape. So I had this hideous equation here. Okay, so, but it's much easier to draw it, so I will do that for you. If one takes this hideous equation and put that on an exam and ask students to Fourier transform, inverse Fourier transform that, some of them will arrive at this answer, which is the correct one. It's not difficult to do, but it requires a page or two. So this is the raised cosine pulse in time domain. And we see here that if alpha is equal to 0, we have cosine of 0 here. If alpha is equal to 0, this one disappears. So this term here just becomes 1, and we're back to the sinc function, sinc t over t. So essentially, if we put alpha, the access bandwidth, to 0, then we are communicating at the maximum rate we can, and then there is only one pulse that works, and that's the sinc pulse. For all other alphas, we have something which is the sinc pulse multiplied with this thing that makes things good for us, as we will see. Okay, So should we draw the raised cosine pulse? So let's draw that in frequency. So we have here the frequency axis here. And we see here the first part is very easy. It's just a constant equal to t for all frequencies less than 1 minus alpha over 2t. So up to 1 minus alpha over 2t, we just have a constant function equal to t. I'll just draw the right-hand side of it, and then it's symmetric, so it would look the same on the other side. I'll fill in the blanks later on. And then it will go down to 0 when the frequency f is greater than 1 plus alpha over 2t. And in between these 2 points, here and here, it's a cosine shape. A cosine, you remember how a cosine looks, of course. It's something like this. It's a half period of a cosine here. So if it would continue, it would become a cosine like this. So that's why it's called the raised cosine. It's a cosine which we lift off the axis with t over 2. So it's quite symmetric here. So t over 2 here, it will happen in the middle here. Okay. So that's the raised cosine spectrum. And just to complete it, it's symmetric on the other side here. So is this a Nyquist pulse? Well, then we should check for the Nyquist criterion. And since we have it now in frequency here, it's easier to do it in frequency. So what we do is simply we take this, which is h of f, and then we take that and we repeat it to the right and repeat it to the left, spaced by the symbol rate, and then just add everything together, and we should have a constant function. So if we move this to the right, it will end up here at, well, let's do it in t here, 1 over t here. And then we will have something that's constant back to this end here. And then it will be a cosine function that goes down like this. So this is HRCF minus RS. And then if we add them together, due to the symmetries of the cosine function here, we simply get a constant function when we add them together. And one can see that all these transition periods add up and everything is nice and so forth. So indeed, it is a Nyquist pulse, okay, because it fulfills the Nyquist criterion. Another way to check that is to simply insert or compute the t samples of the time pulse here. So instead of small t, we put in capital T, capital 2t, etc. And we see that there is only one sample which is non-zero, and that is when t is equal to 0. And in that case, it happens to be t, actually. It's hard to see, but if one takes the limit when t goes to 0, actually this one becomes t. Becomes 1, sorry. It works. Okay. Questions? Okay. So this alpha that's here, we see that the bandwidth here is indeed on the form that we written earlier, right? It's 1 plus alpha divided by 2t. Okay. So this alpha is the same alpha as we had before when we talked about excess bandwidth, so this bandwidth. So this alpha we can use in general if we just want to describe all pulses with some excess bandwidth. And then in particular for the raised cosine pulses, this alpha is the alpha that we plug into this one to get it in the time domain, or up here to get it in the frequency domain. In time, the pulses look something like this. There are many, okay, so the raised cosine pulses, there is one for each value of alpha. So it's a family of pulses, and we pick the alpha that we like. Okay. We know that we want to keep alpha small to have high spectral efficiency. So is there any reason why we want an alpha to be large? And yes, there is, and that's because then certain implementation issues become simpler. So first of all, if we look at the in this curve, the blue curve, it's hard to see, but the blue curve here is the one which is the largest amplitude here, and then goes up here and down here, and then continues with the largest amplitude here. That is when alpha is equal to 0. And we record that for alpha equals 0, so is the raised cosine pulse is just this sinc function here. Now, if you wanted to use this pulse in a real system, what would be the problem with that? Let me give you a hint. What is the duration of this pulse? Is it 2 seconds, 3 seconds, 2 milliseconds, 15 nanoseconds?
Several periods.
Yeah, I mean, it extends forever, right? So in principle, mathematically, it has no duration, or rather, it's infinite duration. So it's not time limited. If it's not time limited, what is the problem with that? Yes?
Do you get bleed over into other pulses?
No, not really, because that's what we avoided here through the Nyquist pulse. So it's not going to interfere with the other pulses, consecutive pulses. There is something else. So when you want to first transmit the first symbol, how long does it take in time? Oh, you have to output the pulse, right? So for sure it takes the pulse duration to transmit that one. And then you transmit the second pulse a little bit quicker, right? But I mean, just to transmit the first pulse takes infinity, time infinity. That's a slight problem, right? It takes infinite time to transmit the first pulse. Okay, so what do we do as engineers? We say, we truncate, right? So we truncate this, but then you have to truncate this such that the majority of it is not affected. So we truncate when it's small, right? When we see that it's decaying like this, but we see also that the blue curve here, the sinc pulse, is decaying rather slowly. Actually, it decays quite slowly, just as 1/t essentially. But we see at the other pulses here, for instance, when we pick a larger alpha, 0.25 for instance, we get the green one here, which decays quicker. Or alpha equals 1/2, we get the red one, and it decays quicker. And alpha equals 1 is almost 0 after just 2t seconds or something like that. So by picking alpha a little bit larger, we are able to truncate more into a shorter pulse without losing the significant part of the pulse. Okay. Truncating means also that we introduce intersymbol interference, which is somehow dependent on how much we truncate, how much of the signal that we actually are truncating away. Okay. So one can say it like this, very simply put, that for implementation issues, it's nice to have a large alpha. For spectral efficiency, we want to have a low alpha. So in the general case, we have to pick an alpha that's a reasonable compromise between spectral efficiency and receiver and transmitter complexity. Okay. Now, maybe somebody is bothered by the following fact here, that we have been talking about H all the time. And what is H? Well, H is the convolution between G and F. So G is the transmitter pulse and F is the receiver impulse response. Okay. So we have talked about how to design the convolution of that, but we haven't really talked about how to select G and F in order for this to work. Okay. Luckily, that's fairly easy to go from H to G and F in this case. And we will do that by picking G and F connected to each other in a very specific way, which is called matched filtering, which is also a very important topic here. Okay, so let's talk about matched filters before we talk about how to design G and F. We need to erase this one. Are there any questions, by the way? No? Okay. Okay, so remember now, we know how to select, or we know one way to select H as raised cosine pulses, or pulses with raised cosine spectra. We know how they look in the time domain. But can we find G and F from this? Well, very often, we choose F, the receiver filter, to be related to the transmitter pulse in the following way. Remember that the transmit pulse is G. For completeness, we want to talk about complex valued pulses here, even though we in practice use real valued signals. But if we have complex signals, we can always conjugate them. So with the star here, it's complex conjugation. And then we want to pick f of t as being g star and then time reversed, so negative t. Remember that when we replace t by negative t in a signal, we simply reflect it in the origin or time reverse it. It's the same thing. Okay. So we want to pick the receiver filter as a time-reversed version of what we have transmitted. Obviously, if the pulse, if we would use, for instance, pulses of this nature or this general shape where they are symmetric, time reversal doesn't do anything, right? It's the same thing. But the conjugation might do something. If it's real valued, then we don't have to conjugate. And then the receiver filter is simply the transmit pulse. Okay, but in the general case, this is what we want to do. This is called a matched filter. So what does that tell us about the Fourier transform of f? Well, I mean, it's the Fourier transform of g star negative t. So can somebody tell me what that is right off the bat? In terms of the Fourier transform of G? I'm not going to hold you to it. You find that in your Fourier transform tables, or you just remember the Fourier integral and you derive it in 30 seconds. But it's actually capital G star of f. Okay. So conjugate and time reverse. If we Fourier transform this function, it happens to be the conjugate of the Fourier transform of G. Okay. Not conjugate and not time reversed. Okay. So H then. What is that in terms of the Fourier transform of G and F? It's the Fourier transform of G convolved with F. This you know, for sure. The Fourier transform of convolution is the product of the Fourier transforms, right? Okay? So here we have G of F times the Fourier transform of F, and the Fourier transform of F is G conjugate F. Okay. And what is G times G conjugate? it's simply the magnitude squared of G. Okay, very good. So now we know that H is the magnitude squared of G. Capital H is the magnitude squared of G. Okay, and we want this to be, say, a raised cosine spectrum. So H subscript RCF. So can anybody suggest a Fourier transform for G to fulfill this? It's not rocket science, so there is no trap in this question. G magnitude squared equals this. So can you tell me a G?
Square root.
Square root sounds great. Why not? Hey, we're on top of things today. Okay, so let's select that. That will surely work. There might be other solutions also, but that will sure work. Okay, and this a pulse G satisfying this equation is called a root raised cosine pulse, right? Okay. This is all well, but can we also actually calculate the time? I mean, the spectrum is very easy. We just take this and take the square root of that, and then we have the spectrum. But the time domain pulse is what we're looking for, because that's what we need in implementation. But it actually turns out that it's not super difficult to find that. So in the frequency domain, the root raised cosine pulse is simply the root of the raised cosine pulse. Okay. In the time domain, we get this expression, which is a little bit more complicated, but it's just a few lines of code. Okay, so it's not so difficult to implement this. And from this, it's obviously the case that if we take G and multiply with itself, we get H. But it's not so obvious that if we conjugate these two, convolve these things with itself, that we get this, right? But we're lucky enough to be able to convolve, or if we have shown this, we have shown this, right? Okay, questions? Okay, so these pulses are used heavily in practice. Okay, so for instance, in 3G cellular telephony, these are used with an alpha. I don't recall the number of. I don't recall exactly the number alpha in this case, but it's something. 0.25, if I remember correctly, something like that. Okay, so to recap now, if we want to avoid intersymbol interference, we want to fulfill the Nyquist criteria. The Nyquist criteria is phrased in terms of H, which is the convolution of the transmitter pulse and the receiver filter. If we use this criteria, which is known as the matched filter criteria, where the impulse response of the receiver filter is related to the transmitted pulse in this particular way, it's a time reversed and conjugated version of this one, then it's easy to find a pulse G that at the end of the day gives a intersymbol interference free transmission. Okay. And then one can use, for instance, these root raised cosine pulses. So we'll take a break now, and when we return, we're going to go back now and look at the receiver implementation in more detail.